Yes, that is recording. I will stop screen sharing and let Adele start the talk, and thank her for giving the first talk in the seminar series.
Awesome. So thanks, Yossi. I'm just going to share my screen. Sweet, awesome. So yeah, just to introduce myself, I'm in my second year of PhD, theoretically at the University of Oxford, but due to COVID, I'm currently physically in Canberra. Also, yeah, so this talk I'm hoping will be pretty accessible. Please do interrupt if you've got any questions or if I start using words that that I should be defining. Okay, so I wanted to talk a bit about triangulation complexity and mapping tori. These are some work that I've been thinking about for the last 6 months or so. And so like one thing that we often do when we're trying to understand manifolds, right, is to study how like different measures of complexity or different measures of size relate to one another, to try to sort of interpret maybe different topological or geometric invariants. So one particularly combinatorial measure of the complexity of a three manifold is the triangulation complexity. So I'll just define that. So first of all, I should say what a triangulation is to me. And this is going to be a bit hand-wavy. So a triangulation of an N manifold. Well, so the motivation here is that on the one hand, you often want to say something like that it's a simplicial complex homeomorphic to N to your manifold, and that's all well and good, but that would mean that that this really natural thing, right? So this, if you glue a square up using these edge identifications, you get something that's homeomorphic to the torus. And sort of the thing that I at least really want to do to triangulate this is just to chuck a line through the middle and be like, great, two triangles, done. But this isn't a simplicial complex because you see that like if you look, because like you're getting, you've got two faces and they're identified along more than one edge. So with that as motivation, we need a slightly broader definition. So a triangulation of an N manifold to me is a cell complex T that is homeomorphic to your manifold, and manifold M, and homomorphism from T to M, where, well, I said that T is a cell complex, but I want a particularly nice cell complex. So a bit more general than a simplicial complex, but like still really nice, where T is constructed by taking a collection of N simplices, because we still do want them to be simplices, right? And we're just going to say we're going to identify them by faces and I mean, you do, like, I'm skipping some technical stuff, you put some technical stuff on that, but we're just going to like identify faces. So anyway, but that's all on identifying faces, but that's all some stuff I don't really want to spend too much time on. So yeah, so then the triangulation complexity of a manifold of, let's say, a closed three manifold, though you can do this a little bit more generally, is the minimal sort of like, we want to measure the minimal such triangulation. So the minimal number of tetrahedra in a triangulation. Okay, so this might seem like a bit of an unintuitive invariant, in that, unlike a lot of things we might talk about, like the volume or measuring lengths of curves, it isn't maybe so intrinsically geometric. Triangulations is something that mathematicians have been thinking about for quite a long time. The minute you want to do calculations, whether that's by hand or using a computer, they're really useful. For example, I'll just move pages. So for example, you might want to calculate, well, first of all, we can do some homology stuff, which is great. You might want to get given a knot, you might want to say if it's the unknot, and that often starts with a triangulation of the knot complement. Or say you might want to like generate lots of interesting surfaces, which you can do using normal surface theory in a triangulation. And so one computer program, Regina, that's a bunch of people contributed to, but I think it's mainly run by Ben Burton up at UQ, is something that lets you like put in a triangulation of a 3-manifold, and then it will spit out like all the information you might want to know about it. So triangulations are really practically useful. One question that I'm particularly interested in is like, what is the triangulation complexity of a manifold? Like, what does that actually measure? What does it mean? Which means I want to relate it to more geometric invariants. But before I get onto that, I might just give some examples of some actual like triangulation complexities of manifolds, because I mean, we should probably check they're not all like 0 or something silly like that. First of all, well, they're not all 0, because just by seeing what you can do combinatorially, like for any fixed number, it hopefully shouldn't be too hard to see that there are only finitely many 3-manifolds with oh, sorry, I should say that I'm going to use the delta of M as the triangulation complexity. That's just a notational note. So there are only finitely many manifolds that have triangulation complexity at most that number, just because there's only finitely many things you can do within tetrahedra. So certainly we can get as high as we like. But what are some examples? Well, one world where we really understand what's going on is in surfaces. So if you take, so I know that I said that definition for 3-manifolds, but I mean, you can write down the analogous thing with surfaces and triangles, and you get a sensible definition. With surfaces, sort of the naive thing to do is, if we've got a surface, we know that we can build that by taking a polygon. So we take a polygon with 4G sides for a surface of genus G. And then we can do edge identifications, right? So I'll just draw a couple on. And we can get the surface of genus G out of this. And so something that you might do is just triangulate this polygon. In this sort of way. So it's not the best drawing ever. Okay, so how many have we got? Well, we see that we get one triangle per edge of the polygon, except that there are 2 triangles that pick up 2 edges of the polygon. So we can see that certainly the triangulation complexity of a surface of genus G is at most, well, 4G sides minus 2 for these triangles that are hitting 2 edges. And in fact, by an Euler characteristic argument, well, this Euler characteristic tells you that you must have at least 4G minus 2 triangles. So this is the best you can do. So surfaces are pretty sorted, I guess with one caveat, which is going to be that so this construction I just drew is only going to work if you've got genus to start with. So the triangulation complexity of the sphere is equal to 2 by this picture. I'm going to claim that that's a sphere. And we can sort of see that it's got to be at least 2 because the triangulation complexity of a surface has to be even, as a triangle has an odd number of sides. Okay, so that's the surface case completely dealt with, which is nice. But as in so many stories, in the 3-manifold case, life gets, well, harder or more interesting, depending on how you look at it. So in 3-manifolds, I certainly can't give you a classification like this. I'd be pretty interested if anyone could. But I can tell you the triangulation complexities of 2 particular 3-manifolds that I like, mostly because they're both 1, and we know it's got to be at least 1. So that's really easy. So 3-manifolds. So what do we get? The triangulation complexity of, the triangulation complexity of the 3-sphere is equal to 1. And so it's enough to just exhibit for you a gluing of a tetrahedron to itself that gives you that. So what's that going to be? Well, I'm just going to draw a tetrahedron. And the gluing I'm going to do is, first of all, I'm going to take these 2 front faces and I'm just going to fold them to identify them. So I'm just going to do that sort of fold, and I'll just draw letters on these to show you what I'm doing. So I'm gluing this F to this F, right? And then this gives me, this gives me a 3-ball with, so this is going to give me a 3-ball where, we've got 2 faces left, so its boundary has 2 faces, and they're just joined like so. So the induced sort of triangulation on the boundary of this is just going to be this one, where we've just taken 2 triangles and we've glued them up, right? And this might take a little bit of thinking, but my claim is that if I sort of do the same thing again, so I just identify these 2 faces, my claim is that I get the 3-sphere. And sort of how you can maybe see that is that if we cut along sort of this plane inside here, we've cut it into 2 3-balls, and all I'm doing is identifying their boundaries by the identity map, which we know gives us a 3-sphere. Okay, so that's nice. Another one, well, this is a 3-manifold with boundary, but the solid torus also gives us one. And this one it takes a little bit more thinking, maybe. In this case, I'm going to take a tetrahedron, and what I'm going to do is, again, I'm going to glue these 2 front faces together, but this time around I'm going to glue with a twist. So what I'm doing is, if I draw F here, I'm putting my F this way. Yeah, so I've definitely got it. So that's, you can sort of see that if you spin it, I've flipped the orientation. So I'm going to end up, so that's good, because we need to make sure that we do compatible orientation things. And my claim is that this is homeomorphic to the solid torus, but I don't really want to talk about that too much. There's some really neat pictures if you look up 1 tetrahedron triangulations of the solid torus of like what this actually looks like. Okay, so that's some examples, but I claimed that I was going to talk about relating the triangulation complexity to some more geometric invariants. So we should probably talk about that. Okay, so one, well, I guess this is a bit more topological again, but one thing that is a pretty natural question to ask is how does the triangulation complexity behave under connect sum? So just to quickly define that, if we have two N manifolds, then the connect sum of these manifolds is constructed by removing an n ball from each, right? And then we have two resulting sphere a resulting sphere boundary component or each of them, and then we're going to identify the resulting boundary components. So, for example, if we take the surface of genus G and connect sum it with the surface of genus H, well, our genus is going to add. Because, yeah, I guess, in effect, you're just, say, taking two tori, for example, and then you're just sort of taking out a little patch on each of them and like extending sort of and you can think of it as sort of extending a tube across and gluing that up. So we're going to get genus 2. So how does triangulation complexity behave under this operation? So when I first thought about this, I thought for sure we're going to get it that it's subadditive. Okay, so for sure we're going to have this. Oh, sorry, that's not how you write these things. Right, because like in my head, how that proof would go, right, is that you're just taking out a tetrahedron from each of them, identifying the boundaries. I mean, in fact, in that case, you're subtracting 2, right? Like, I mean, you're removing a tetrahedron from each and you're identifying things. So you're going to get a number of tetrahedra that you started with minus 2. But this is false because, I mean, this is why I was a bit careful with my definition at the start. So the closure of a tetrahedron in M is not necessarily a 3-ball. Because we can glue multiple faces to the same other simplex, we might find that, like, say, some of our vertices are identified or some of our edges are identified. Like, we're going to get something. Well, I mean, for an extreme example, we triangulated the 3-sphere with one tetrahedron before. The closure of that tetrahedron, certainly not a 3-ball, it's the 3-sphere. So something where we can see this happening is in the surface case. So I said before that that if we connect sum the torus with itself, we get the genus 2 surface, right? But if you think about this minimal triangulation of the torus, right, which is this, yeah, and then if we remove one of these, so say I'm going to keep this triangle and cut out the other one, okay, then what do we get? Like, what is this thing? Well, we know that sort of this edge here is really just like the edge below, and this edge here is really just the edge to the side, right? So we can just drop those entirely because we already have them in, except that we have one piece of information that we're missing, which is that all our vertices are the same vertex. So it's this triangle, but with all the vertices identified, which I am quite bad at drawing. It's sort of like this thing. One, two, and then sort of one more at the back. It's sort of like a parachute. Is how I think of it. Like, you know, like you've taken a handkerchief and you've pulled the corners down. And so, in fact, if you take two of these and you identify them along their boundary components, what you get is so this connects so this thing connects itself is in fact, I mean, you've just taken two triangles where all the vertices are identified and then glued them up, which just takes us back to our original triangulation of the torus. Okay, so we're seeing here like this real failure of what we might expect would happen. And so in fact, what you get in the surface world is a sort of straightforward calculation, is that the triangulation complexity of the surface of genus G connects some with the surface of genus H, which just adds the genuses, is equal to the triangulation complexity of the surface of genus G plus the triangulation complexity of the surface of genus H plus 2. So it's not sub-additive at all. In fact, it's super additive. So something that I'm quite interested in at the moment is what happens in 3-manifold world. And I don't actually have an answer for that. I think we conjecture that you get similar behavior where it's this like where you get like the sum plus a little bit, but still thinking about that one. So this is open as far as I know. Okay, but I did promise you geometry, so I should probably get into some geometry. All right, so I'll just change the page. So here's something that's really geometric. Let's talk about hyperbolic volume. Yeah. Sorry, Yossi, what time am I going to?
Probably like another 15 to 20 minutes, I'd say.
Yep, sweet. Awesome. So let's talk about some hyperbolic volume. So let's suppose we have a closed, orientable 3-manifold, right? And let's suppose it's hyperbolic. So just quickly, what does that mean? So it means that similarly to the definition of just a regular 3-manifold where you've got these outlets of charts and you require that your transition maps are continuous, it means that we have an atlas of charts into hyperbolic 3 space with transition maps that are hyperbolic isometries. Right. Okay. And this is a pretty, like, this might seem like a pretty constrained thing, but this is a really big, interesting class of 3-manifolds. I think there's a sensible way of saying that most 3-manifolds are hyperbolic. For some definition of most, that's true. And in particular, I really like hyperbolic 3-manifolds, so I'm going to talk about them. So as I specified that M was going to be closed, an equivalent definition is that M is homeomorphic to some quotient of hyperbolic space by a discrete lattice. So where gamma is going to be a discrete subgroup of hyperbolic 3 space of isometries. All right, so we've sort of ported across a hyperbolic geometry, and so for a given hyperbolic structure, we can ask what is the volume of this geometric object, and by Mostar rigidity, the hyperbolic volume of M this was hyperbolic volume, is, and this is quite surprising, it's not just like an invariant of your particular hyperbolic structure, it's in fact an invariant of your topological manifold, which is pretty neat. So one result that we can get with triangulation complexity out of this at least it's a sort of easy corollary of some work by Gromov and Thurston, is that the triangulation complexity of M is at least the hyperbolic volume of M, and then we divide out by the volume of like basically the biggest geodesic tetrahedron you can get in hyperbolic 3 space, by the volume of a regular ideal tetrahedron in H3. So one way of interpreting this is saying that if you can find a triangulation where all of your tetrahedra are like big in your geometric structure, then it's probably a pretty good one in terms of being minimal. Okay, so that's some stuff. And what we might hope is that maybe we get an upper bound as well. Maybe your triangulation complexity sort of looks like your volume. But in fact, this is false. So, right, so what we might hope is that these are sort of proportional in some way. The answer to this is not at all. So how I'm going to show this is, so we said earlier that there's only finitely many 3 manifolds with a given triangulation complexity or lower, right? And I'm going to show you an infinite family of 3 manifolds, or with bounded volume, which tells us that we must be able to find a 3 manifold with this bounded volume, but with triangulation complexity as high as we like. Okay, so that's the plan. So we can do this using hyperbolic Dehn surgery. So what's that? So if N is a finite volume hyperbolic manifold with, this time with boundary, with one boundary component that's going to be toroidal. So for example, the complement of a hyperbolic knot, sort of by definition. Now, Dehn surgery, what's that? On N is gluing in a solid torus along the boundary. So we're getting a closed 3 manifold out. And the choice we have here is in our gluing map. And it turns out that this is parameterized by a choice of slope, which effectively says, like, in our boundary component, which slope are we going to glue a disk into? And this slope is a rational number. So the theorem, which is Thurston's hyperbolic Dehn surgery, is that for all but finitely many slopes, the resulting manifold, which I'm going to write as MP over Q, has a hyperbolic structure. Furthermore, these have bounded volume, which is what we wanted. And we might worry that maybe we're just getting the same manifold, like hyperbolic manifold, over and over and over again, but in fact, this isn't the case. So we get infinitely many topological manifolds. So this is telling us that we can't get this relation. Okay, great. So in the last 10 minutes, I just want to talk a bit about mapping tori, which was the other bit of the title. So this is something where we want to connect the triangulation complexity of our three manifold to the dynamics of a particular homeomorphism. So let's suppose that sigma is a closed surface, and phi sigma to sigma is a homeomorphism. Okay. Then the mapping torus of this particular homeomorphism, which I'm going to denote by m phi, is well, what do we do? We thicken up our surface and then we glue up by this homeomorphism. So I'm going to write that as our surface cross interval where we're identifying the boundary components by this homeomorphism. So it's a closed three manifold. So a question, a pretty general question you might ask is, how does the dynamics of our map relate to the geometry of our three manifold? Which I think is a pretty interesting question. In general, you're going to have lots of different maps that give you the same three manifold, which is to say that a given three manifold is in general going to have lots of different fibrations. And something that I'd be really interested to know about is like what actually connects these maps. Like if they're going to give you the same three manifold, they feel like they should have something in common. But that's something that I don't know the answer to. Okay, so a nice thing about mapping tori is that we can give a really easy lower bound on our triangulation complexity. Sorry, upper bound on a triangulation complexity. So an upper bound. Okay, so we're going to do this in terms of the action of our map on a particular on the triangulation graph. So so let's suppose we've got a triangulation of our surface. Now a 2-2 Parkner move on a triangulation of a surface is well, we take two triangles and then we like pick the other way of triangulating that quadrilateral. So that's a move. And then it's a fact that if you've got two one vertex triangulations of the same surface, you can move between them using these 2-2 moves. All right, so just move down a bit. So what this is to say that if I define the triangulation graph of our surface to have vertices that are triangulations of a particular surface and edges that are 2-2 moves, then this fact is really just saying that this graph is connected. Right, so this is connected. So how does this relate to triangulation complexity? My claim is going to be that we can control that the triangulation complexity is upper bounded by the following thing. So one more definition. The translation length of phi in this particular graph, so our map acts on the surface, so it acts on the triangulations. The translation length of it in this particular graph, which we're going to denote as follows, is the minimum distance that it moves something. Okay, so that's this thing. So we're going to, right, this quantity. Great. And my claim is that the triangulation complexity of my mapping torus is at most some constant that depends only on the surface, not on the map, plus this translation length. Okay, so how am I going to prove this? Well, the connection between these like triangulations with tetrahedra and these 2-2 moves is that I can perform a 2-2 move by layering tetrahedra. So if I've got a particular triangulation of my surface, well, maybe this is some part of it. I don't know. I'm pretty uninventive with these. There's like a whole bunch of triangulations of triangles, you know. Then say that I want to do a 2-2 move on this bit, right? Well, how can I do that? I glue on I'm going to glue on the tetrahedron that sort of looks like this. So what I'm trying to draw there is that I've got so hopefully you can sort of see that this is the same thing as this, right? So I'm just gluing on a tetrahedron like that. And you can see that the induced triangulation on the resulting surface boundary is going to be exactly what we get when we just perform a 2-2 move. So this suggests that we should do the following picture. So we're going to start by taking my surface sigma, and we're going to just find some triangulation of sigma cross interval where our induced triangulation on the top and bottom are the same, right? So this is just a thing. And then what we're going to do is we're going to get to a triangulation, then we're going to triangulate the surface cross interval so that we get phi of our triangulation on the boundary down the bottom. And we're going to do that by thinking about the path from t to phi of t in the triangulation graph. And we're just going to, so we've got like t here and phi of t here in my triangulation graph, and there's some path between them, where each of these is a 2-2 move. And for every one of these edges, we're just going to stick on a tetrahedron to like execute these 2-2 moves. Okay, so this corresponds to 2-2 moves here. So by doing this, we've obtained a triangulation where we've got a certain triangulation at the top and phi of that triangulation down the bottom. And then at this point, we just glue up by phi, right? And we've got a triangulation of our mapping torus. Yeah. So and so what do we pick up here? Well, we pick up some constant number of tetrahedra here, just to sort of kick things off and make sure that we don't end up with a patch that doesn't actually have any like 3-dimensionness to it. And then here, well, if we pick our triangulation well, we're going to achieve this minimum in terms of the number of tetrahedra. So this gives the claim. So in my last 2 minutes, so one thing that you might hope is that this naive thing is like a good way of doing stuff, that actually it isn't so bad. And in fact, this is the case. So this is proved, I guess, 2 years ago now, which is that when your mapping torus is hyperbolic, which really I'm saying that phi is pseudo enough of, but I don't really want to define that. There are constants C and D depending only on your surface, such that the statement here is that such that this naive way of doing things and the true triangulation complexity never get too far apart. So they bound the ratio. So that's great. And then just to mention the slight, I guess, extension of this that I've been working on is the following statement, which is that if your surface happened to be the torus and phi is a knot of, which means you get a particular geometry of your resulting free manifold, then if we then we might want to think about what happens if we compose by a Dehn twist. So that's this sort of. So what happens if we compose our homeomorphism with a different homeomorphism, and in particular with this homeomorphism? And the result that we get is that, again, there are constants such that the triangulation complexity of the mapping torus of phi composed with a Dehn twist, right, where I said that this is the Dehn twist, is not so far away from a similar naive thing that you can do by layering tetrahedra. Okay, great. I think that's everything I wanted to say. Thank you.
All right, thank you so much. If everyone could join me in thanking Adele for starting off. Does anyone have any questions?
Yeah, I have a question. Sorry, my camera doesn't work, but I guess so. In your definition earlier, and in a lot of the examples we've looked at, you've been looking at triangulation complexity with finite triangulations, right? So they don't have any vertices on boundary components. They're not ideal triangulations. It doesn't seem like anything would really stop you from thinking about ideal triangulations. Have they been like a part of your interest at all?
That's a really good question. Yeah, so ideal triangulations are certainly something that, like, as you say, makes sense to study. And I think Stefan Tillman's certainly someone who's thought about these things. So Stefan Tillman, thinking about like sort of similar things we're doing. I think we are doing like mapping tori on like punctured surfaces, that sort of stuff. They're not something that I personally have thought about very much, but yeah, I think they're also a really interesting area.
Yeah, I guess really relevant to this sort of result is if Stefan's looking at like punctured surfaces, then what I guess like a similar approach might be if you sort of drill out one of the fibers that you're working with here, like you've got your pseudo-analysis homeomorphism on the torus, and you got some fibers coming through that. If you just sort of delete it from the manifold, then you get like a boundary component, and maybe like a result like this still holds despite the fact that the manifold is like entirely different. I would be interested in something like that. I guess this is an expression of interest in your research rather than a question. Yeah,
no, I guess to talk to that a little bit. And yeah, no, I agree. That'd be very interesting. One thing that, so this result from like Lackenby and Purcell talking about when your mapping torus is hyperbolic.
Yeah.
The obvious thing that you want to do, right, is talk about like, let's just talk about like mapping tori, full stop. Yeah. And so the abstraction to that, so we know that phi we can classify as pseudo-Anosov or reducible or periodic. And so I've talked about the pseudo-Anosov case. And so when phi is pseudo-Anosov, we're good. When it's periodic, it's, I mean, up to a finite cover, it's just your surface across the circle, so that's easy. And the reducible case, which is when you fix a multi-curve, is turns out to be the hard one, because you're fixing this curve, and as you say, the thing that is sort of natural to do would be to drill out the torus that you get from that curve. But then the question, and then we can understand the triangulation complexity of each of those pieces. Okay, I'm not sure if we can, but like it seems sort of approachable. But then understanding how the triangulation complexity changes when you then try to glue up along that torus is pretty hard. I don't know how to do that. But it's something that'd be really interesting to know.
Yep, thank you. Yeah. And thank you for the talk.
Thanks.
Awesome. Any other questions?
Yep, I have a question if I want to jump in. Yeah. Hey, Adele. So I was just wondering, maybe this is probably not even related at all, but I was just wondering if the triangulated complexity is actually related to, say, topological entropy in any way at all, since it seems like many of these mapping tori things are dependent on the homomorphism, the type of homomorphism that you're picking.
I'm sorry, this is going to be a very unsatisfactory answer. I don't know, because I don't think I know what topological entropy is, to be honest. So
Okay.
maybe we can talk about it another time.
Yeah, yeah, we can.
It may well be. I've got no idea. Yeah.
All right, if that's it, I will create about 5 breakout rooms for those that want to stick around. It is, 5 to 11, so I understand that people have got lectures, classes, other things to do, sick of hearing my voice, which is fairly reasonable. I'll create that. I will briefly stop